I'm Kenjiro Terada from Tokyo University. Today, I'm going to talk about the exploration of some predictive disaster simulation by using the finite element method and material point method. Unfortunately, Japan is a disaster-ridden country. Okay? We are always challenged by some sort of disasters. For example, we have earthquakes and tsunamis, which occurs with low frequency. In summer season, we have lots of typhoons and floods. Because of that natural disasters, we have also slope disasters, such as sediment disasters, including the mudslide, mud flow, and rock slide. In spring season, we also have the snow avalanche. So this is actually the landslide which occurred in Japan. Then, as you can see, we had the catastrophic failure. Okay. An important aspect here is that the solid structure made of soil can flow as a fluid. Okay. This is one of the phenomena we are concerned with today. Okay, so with this background today, I'm going to talk about our current status of numerical simulation of disasters. Okay, then for that purpose, we extensively utilize the finite element method and also the material point method, depending on the intended use. Okay. Okay, the problem we are target today includes the one snow avalanche and three kinds of landslides and dike collapse. The last one is more complicated than others because we have to deal with this water flow coupled with the soil motion. Okay. So to make our numerical simulation more predictive, we have improved the stabilized finite element method in terms of material modeling and also the representation of the free surfaces and the material point method for the solid fluid mixture. Okay. So let's begin with the simulation of snow avalanche using the three-dimensional stabilized finite element method combined with the phase field modeling for the free surfaces. Okay. In the numerical simulation of the snow avalanche, the problem is that we don't have the appropriate material model. Okay. So even if we apply the constitutive equation that can be utilized for the solid mechanics, it's very difficult to determine the material parameters. Okay. So if we have no choice, we sometimes treat the snow as a Bingham-type fluid. Okay. As you know, the Bingham-type fluid has strength here. Okay. Then for the strength evaluation of the snow, we introduce here the Coulomb yield criterion. Here is the C is the cohesion and pressure and internal friction angle. And then here, so the strain rate that is invariant of deformation rate that can be explicitly calculated from the velocity field. Here is the material response is illustrated. Then, in combination with this material model, we utilize the three-dimensional stabilized finite element method with unstructured mesh that enable us to simulate this kind of snow avalanche. This also enables us to represent complicated geometries of landforms like this. And also we can evaluate the three-dimensional behavior of snow avalanche. Okay. So this is the governing equation for the stabilized finite element method. Here is the Navier-Stokes equation with continuity equation. This is a very standard setting for the computational fluid dynamics, except for this non-Newtonian viscosity that depends on the shear strain rate. We simply discretize this equation by using the linear tetrahedron for both velocity and pressure field. And to suppress the advection and the pressure field, we utilize the SUPG and the PSPD method respectively. This is the corresponding discretized equation by using the stabilized finite element method. To represent the free surface and its movement, we employed phase field method. That is, free surface is captured by the advection of the phase field function phi p in the fixed mesh. Here is the illustration of the phase field function. You can see here phi p equals 0 corresponds to the gas phase. The value 1 corresponds to liquid phase. The intermediate value 0.5 represents the interface here. To capture the movement of this interface, we solved Allen current equation for the modified conservative system here. Here we have the f that can be calculated by using the value at the previous time step. Okay. To suppress the instability due to the advection, again, we utilize the stabilized method, SUPG method. Here, epsilon is the mobility associated with the stabilized parameter, and also delta is the interface width that can be determined by the mesh size. Okay. By using the nodal value of this phase field function, we can calculate the density and the viscosity by this equation. Here, liquid phase is assumed to be non-Newtonian, but gas phase is assumed to be Newtonian in this case. This is the target problem. The snow avalanche that occurred in the vicinity of the national road here in Japan in 2011. This picture shows the actual appearance at that time. Then we installed additional retaining wall. So our concern here is to examine the effect of the additional retaining wall here. So for that purpose, we conducted 2 cases of numerical simulation for comparison. One is the case 1, the simulation with existing retaining wall only, and the case 2 with both existing and additional walls. Let's see the first example result. This is the result of the case for the case 1. As you can see here, the snow gets over the retaining wall here and flow out extensively on the road, and the national road was blocked out. This is actually exactly the same situation at that time. Okay. So we can say that the presented simulation is capable of reproducing the actual snow avalanche. Let's see the next case here with the existing and additional retaining wall. Okay, then we can conclude that amount of the overflow on the road is decreased thanks to the additional retaining wall. Then we can also conclude that the stabilized finite method with Bingham type fluid model, which was enhanced with the phase field model for the free surface model, may be reliable tool to evaluate the 3-dimensional behavior of snow avalanche. Then by using the same method, we want to try to solve the landslide problem. This is a simulation of the full Langat landslide occurred in Malaysia. In this simulation, in this example, the simulation is followed by the visualization techniques for some reason. Let me introduce a typical landslide in Malaysia. Okay, here is a hilly area. People cut the slope like this, then construct the houses like this. Okay, but they usually don't construct retaining wall here. Okay, this is the problem. Okay, then as a result, landslide occurred due to the heavy rainfall in 2011 in Pulau Langat in Malaysia. Because there was an orphanage here under the cut slope, 15 children and the caretaker were killed by the landslide. This kind of housing activity near steep cut slope without retaining wall is commonly seen in Malaysia. This is the big problem. The situation increases the risks of landslide disasters. So the effective way to solve these issues might be construction of countermeasures, the development of disaster prevention maps, that is called the hazard maps, and also the laws for housing activity. Last one is the disaster education. Especially for the disaster education for the residents, the virtual experience by numerical simulation must be effective. Okay, so for that purpose, here is the simulation. We try to simulate the mudslide to illustrate hazard in the case of without retaining wall to show the hazard to the residents. Okay. Here is the site, Pulau Langat in Malaysia. Here is the orphanage that was attacked by the landslide at that time. And here is the result. Okay. It seems fine. It's convincing or effective for disaster education. Maybe the answer is no, because the movie is very not realistic at all. So although the simulation might be successful, the residents cannot recognize it as their own situation. Okay. So for that purpose, for the effective awareness training of landslide, we had an eye on the elaborate visualization techniques by using dedicated software. In this study, we utilize Unity software. Okay. Then let's see the result of the same simulation. Okay, this is a movie made by Unity. Okay, as you can see, the result becomes more realistic in the sense that we have their houses visualized in the result. Then the community residents recognize this kind of landslide as an express threat for their lives. Okay. But most of you may criticize the simulation result and visualization result here. Oh, sorry. Yeah, maybe here. Please create the sound. What? What is sound? This is the movies. What? How can I delete sound? These are the movies, the same simulation result viewed from a different angle. Okay. We can choose the effective. What? No, I switched off already.
In Japanese, I don't know.
It's ended, okay. So maybe most of you criticize this simulation result because why the houses are not damaged by the mudslide. This is a big problem we have to challenge in the future. Although I haven't yet risen to a certain level at the stage. The numerical simulation, along with this kind of numerical visualization, may be effective for the education purpose, but not predictive at all right now. So, what is the predictive disaster simulation? When will a certain disaster occur, and where it is, and why does it occur? And lastly, how much damage will we suffer from the disaster? Okay. So as you can imagine, such prediction much more difficult than the numerical analysis of engineering product. So in this context, let me show you the simulation of landslide caused by 2006 Kumamoto earthquake by using the material point method in this case. Here is the Japan Islands. Here we have the Kumamoto prefecture that was attacked by the earthquake. By the way, I came from Sendai, and here is Tokyo. And also we have Yokohama. Why Yokohama? We have WCCM 2022. Please come. I'm sorry, this is just advertisement. Let's go back to my presentation. This is Kumamoto. The 2016 Kumamoto earthquakes killed at least 15 people and injured about 3,000 others in total. We should have predicted this kind of disaster to reduce the victims, number of victims, but we couldn't. Okay, so maybe you know that earthquake forecast is almost impossible. Nevertheless, we should have known where the hazard or risks of mudslide would present at the time, and also we should have known how much damage we would suffer at the event of possible earthquake. Okay. So this is a satellite picture of disaster-affected area by the Kumamoto earthquake. Before the earthquake, okay. Here is a national road along here. This is a mountain. Here's the Aso Bridge here over the steep and deep valley here. This is a picture after the earthquake. As you can see, we had a mudslide due to the excitation of the earthquake. Here, the Aso Bridge collapsed. Okay. So if there was a possibility of the mudslide at the event of a specific earthquake, we should have predicted the relevant risks by the elaborate numerical simulation, but we couldn't at that time. So the prediction simulation was conducted only after the earthquake. Okay. For the validation purpose, we compare the result with the actual situation. Okay, it seems to be fine, but after the validation successfully made, the adopted method of numerical simulation becomes an effective prediction tool. Okay, but reality is not. In fact, the simulation is far from satisfactory because it answered neither where the mudslide would occur nor how much soil mass would flow. In particular, the result doesn't answer why the earth bridge collapsed. Okay. So actually, this simulation was done by the material point method. Most of you know what it is. Material point method is known to have both features of Lagrangian and Eulerian method by combining the set of material points and Eulerian grid here. Lagrangian particle corresponds to the integration points in the finite element method and can be used to store deformation history at the material points. Okay. On the other hand, Eulerian grid in the material point method is used to solve the equation of motion. Okay. Before solving the equation of motion, we have to map the physical quantity at the particle onto the associated node by this equation. And here, then after that, we can solve the equation to have the updated velocity field. Then we can reset the Eulerian grid. Then by using the updated nodal value, we can interpolate the physical quantity at each particle this way. Then after that, the particle can be advected by using the updated velocity field. Okay. Okay. Then in the numerical simulation I have shown, I employed Henke type hyperelastic model to represent the elastic deformation of the soil. For the plastic deformation of the soil, I employed the Drucker-Prager yield function along with the plastic potential for the non-associated flow rule here. Here we have cohesion that determines the strength of soil. If we introduce cohesion as a decreasing function of saturation, we can conduct the numerical simulation for the progressive failure due to the effect of excessive water content. For example, let's see the deep-seated landslide in Kii Peninsula in Japan. Okay. Here we had a mudslide due to the excessive water content after the heavy rainfall. We prepared the digital elevation model whose original data were available in GIS software. Then analysis region was extracted from this side, okay, to generate the model of the material point method. The purpose of this simulation is to see the effect of working wall installed here. Then this mountain is composed of the upper layer and the lower layer. The soft soil is assumed for the upper layer, and the lower layer is assumed to be made of rock. Also, the interface is supposed to be a weak surface in this simulation. Then we expect a two-stage sequential process. That is, first, the groundwater level is elevated to cause a decrease of soil strength according to this decreasing function. Then, at a certain time, the part of mountain began to slide. Here's the result. First, groundwater level is elevated like this. Then, gradually, the soil degrades. Okay. At a certain time, part of mountain begin to slide like this. As a result, the national road will become out of service for some days. This is actually the same situation that occurred in Japan. Okay, the numerical simulation I have shown up to now are relatively easy because they are the single-phase problem. Okay, to make our numerical simulation more predictive, we have to concern with the water flow coupled with soil motion. Okay, we have to consider this kind of phenomena. Okay, here is the example of the sediment disaster. The sediment disaster is kind of how can I say, a landslide. Then we have to consider the solid mixture formulation in this case. At the same time, this phenomena involve the bidirectional transition between the saturated soil and soil-water mixed liquid. That is, in this transition process, we should consider the elastoplastic behavior of soil and gyration, non-Newtonian liquid, and also quasi-Newton liquid, that is soil-water mixed liquid. So we have to consider this kind of transitions. Okay, in order to represent this kind of behavior of solid fluid mixture, there seems to be two ways in the literature. The one is the three-phase model, and the second one is the two-phase model. In the three-phase model, each particle has information about the soil, pore water, and pore air in common. Because of this feature, we can apply the implicit time integration method, okay, to make the equilibrium be satisfied strictly. On the other hand, in the two-phase model, we introduced the two separate layers of soil and water particle. Because of that, we have to apply the explicit time integration scheme. Okay. But since the equation of motion for each phases are connected only through the mutual interaction force, we can apply directly the various schemes in computational solid and fluid dynamics. Okay, so today we confine ourselves into this model to simulate the Dike collapse with fluidization. Okay, in the two-phase modeling of the solid fluid mixture, we usually assume that the soil grains, this mixture is composed of soil grains and pore water like this. Then, as usual, we apply the mixture theory to combine the governing equation with this, the partial densities here. These are the equations of conservation mass for the solid phase and water phase. For the solid phase, we usually assume the incompressibility of soil grain, so we can delete this term. Okay, but in the literature, people try to deal with the water phase as the slightly compressive fluid. Okay, so in that case, we have to evaluate the pressure of the liquid phase by this constitutive equation. As a result, we have the continuity equation for the liquid phase of this form. But because of the large value of this Vark modulus of the liquid phase, we may have the numerical instability. Okay. So to avoid such instability due to the high value of Vark modulus, we simply assume that the water phase is also incompressible. This is the standard setting for the computational fluid dynamics. So as a result, we could have continuity equation mixture like this. So this is the momentum balance equation for the solid fluid mixture. Here we have the mutual interaction term here. This can be represented by momentum exchange between the soil and the water phases like this. Here we have the effect of buoyancy of the miscible mixture, and also here the interaction forces are caused by the viscosity. These forces can be evaluated by using the linear Darcy law in a region with relatively low Reynolds number. But for the relatively high Reynolds number flow, we have to apply the Darcy-Forchheimer law that involves the nonlinear term of this form. Okay. For the temporal discretization of the momentum balance equation, we simply apply the fractional strip method. This is very standard for the computational fluid dynamics. Here is the intermediate velocity and the velocity field at the current time step. Then by taking the divergence of these two equations, then substitute into the continuity equation, we could have the pressure Poisson equation like this, to implicitly solve for the current pressure field like this. Yeah. Now, for the spatial discretization of the pressure Poisson equation can be done without any special treatment. So let's move on to the next slide. But also the spatial discretization of the momentum balance equation, the current velocity is also standard. So nothing special here. So let's move on to the next one. But the spatial discretization of the momentum balance for the intermediate velocity here, we have to deal with this term with special attention because we have the mutual interaction form here. To evaluate this term, we applied a special integration scheme here, like this, in consideration of the volume fraction of solid and liquid phase each cell here. This volume fraction can be evaluated by this formula here. The key factor here is that the nodal volume fraction of phi hat here, that can be mapped by this formula here. That is a special mapping formula for the volume fraction that was defined by the ratio of the particle volume in a cell with respect to the cell volume here. Here we have the volume, okay, of each particle instead of mass here, unlike the standard mapping formula for the velocity field. Also, to represent the multi and the single phase state within a cell, like this here, we applied volume integral of the physical quantity by using the interpolation of the volume fraction of each phase by using this formula. Okay, let's see some numerical example. In order to see the appropriateness of the incompressibility of the fluid phase, I conducted the benchmark problem. This is very famous dam breaking problem. As you can see, if we assume the causal incompressibility for the liquid phase, we have the numerical oscillation of pressure like this. Okay, overall pressure, although the overall motion seems to be fine. On the other hand, if we assume the incompressibility for the liquid phase, we could obtain the appropriate solution like this. The advantage of the material point against the other method may be that we can choose any kind of the constitutive equation that can be used for the solid materials. Okay. So up to now here, this is a standard model for the soil. I already explained it. But in the case of fluidization, we have to consider the damage effect. That is, especially for the expanding state. That is, we assume that the soil loses its stiffness when it loses its yield strength, like this here. This is the yield strength. But we also can take another formulation with similar but different idea. Here is the special plastic potential with porosity-induced damage. Here we have the equivalent stress. Here is the flow stress that is decreased according to the value of the porosity here. This is, we say that the porosity-induced damage. Okay. This behavior is illustrated here. Okay. This is the porosity, and this is the flow surface. Let me show you the effect of plastic potential we employed here. We conducted the simulation of sedimentation after the large motion and fluidization. As you can see, the model of the drag-plug plasticity without damage effect, we couldn't obtain appropriate behavior like this. On the other hand, with the drag-plug plasticity and with damage effect, we could obtain appropriate behavior with volume of the deposed soil is preserved like this. Okay. So also the accuracy of the material point method strongly depends on the accuracy of linear basis function. Okay. Now if we, they strongly depend on the basis function. If we employ the basis function that is commonly used to finite element method, we may suffer from the instability. In fact, when the material points are vectored across the grid surfaces, interfaces, a numerical oscillation occurs due to the discontinuity of the basis function. That is, we call that the cell crossing error in the material point method. To avoid such instability, there are some remedies in the literature. This GIMP method may be one of the choices. But in this study, we employ the three-dimensional third-order B-spline function to reduce the effect of the cell crossing error. Okay. So let me show you the performance of B-spline function by solving the stability problem of slope, the embankment, this one. Here is the embankment we are concerned with. By changing the height of this embankment, we have the relationship between the safety factor and the displacement at the top hill here. Okay. As you can see, the result of the with the linear and the B-spline function compared here. You can see the safety, when the safety factor is less than 1, we have the rapid increase of subsiding displacement like this. But here, the result with linear basis function is much stiffer than that of the B-spline function. At the same time, we can see here, the deformation with the linear basis function is not so appropriate like this, because we don't have sharp profile of the slip line here. On the other hand, we could have the appropriate result. So let's demonstrate the capability of the proposed method in representing the bidirectional transition between soil and soil-water mixed liquid. Here is the water channel. For that purpose, we conducted the experiments. Okay. Sandpile experiment. Here is the water channel, and we put the sandpile here. This sandpile is made by vertically lifting the mold filled with river sand like this. Then so that the solitary wave is generated by the wave maker to collide against the sandpile here. Here shows the result. As you can see, the wave washing the pile and transporting some parts. This experiment repeated several times with the same condition, and almost the same result was reproducibly observed. So in order to simulate this experiment, the whole numerical simulation divided into 2 stages. At the first stage, the preliminary numerical simulation is conducted in this region here. In the first stage, we utilize the linear basis function because the non-rectangular domain here is not convenient for the B-spline function. Then, to generate a solitary wave makeup represented by the rigid particle moves downward 0.24 meter at a constant velocity in 0.5 seconds. This is the profile of the solitary wave at the end of the first stage. That is used for the initial profile for the second stage simulation. Here is a bird's eye view of the channel model. Then here is the result. Let's see the more big picture here. Total time was this 5 seconds. The time increment was 10 to the minus 4 seconds. As you can see, some part of the sandpile was washed out by the water flow and distributed downstream to form a long tail like this. These are the top and side view of the numerical result in comparison with the experiment. Okay. As you can see, the characteristic behavior of the isolated sand are well represented. And also some portion of the sandpile was swept away diffusively downstream right after the wave collision, but gradually piled up in the form of the streamline. The profile of the sandpile in the snapshot agree with the experiment result to some extent, as you can see. Also, we can make a quantitative comparison between the simulated outer surface after 5-second calculation and the experimental result that was measured by the laser distance method. That, as you can see here, top portion of the sandpile is sliced off, and some parts of the sand particle deposit on the downstream here. Then let me show you the last example, that is the dike collapse by water flow. This is a setting. Here is the dike we are concerned with. This dike is composed of 4 material here. These are the material parameters we assumed here. This region is filled with water initially, and we have inflow of the velocity of 0.5 meter second. Okay. This is actually 3-dimensional simulation, but the result is the side view. This is the dike, this is the water flow. As you can see, the dike is gradually scraped away. But as you can see here, the washing is not uniform. Some masses are swept away intermittently. Okay. This is a kind of instability, okay, that can be seen in the actual experiment, although I haven't yet conducted this experiment yet. Let me conclude my presentation. I have explored some example of hopefully predictive disaster simulation and related numerical techniques associated with the finite element method and material point method. These are listed here. Was it predictive? Unfortunately not. even far from predictive at the current stage. But our mission should be to make disaster simulation more realistic, reliable, and predictive. Okay, thank you for your kind attention.